Number 40, differentiating the exponential function, which isn't too difficult. The derivative of basically of e to the u using the chain rule approach, where u is a function of x or whatever variable t. So the derivative of e to the u is e to the u du. So notice we don't change that exponent. So the derivative of e to the x cubed is going to have e to the x cubed in the answer, but it's also going to have the derivative of that exponent in the answer. And I just move this out front because usually answers will look like that. Just to make it look a little, it would look a little weird to put the 3 after the e. So the derivative of x cubed is 3x squared, and then your e to the x cubed, there it is. So that's all there is to differentiating e's. Now here's one that involves a product rule. I'm just labeling what order of the product rule I'm using. Because the product rule is plus, you can go in either order. So it shouldn't be too confusing, even if you're, solving a problem that's in multiple choice format. You would just see that maybe they're reversed from what you did. That's all, because you have complete flexibility mathematically to do that because of that plus sign. So I'm just showing you what I did. So f prime g would be the derivative of x cubed, which is 3x squared, times the g itself, which is e to the x squared, plus the f, which is x cubed, times the derivative of e to the x squared, which will be e to the x squared. I put in parentheses to make it look a little neater there, times the derivative of that exponent x squared, which is 2x. Now you see I combined the x's, make it x to the fourth, put the 2 up front, make it look a little better, and we have 3x squared ex squared plus 2x to the fourth ex squared. I guess if someone really wanted to, they could factor out an e to the x squared, and you could factor out an x squared if you wanted to. I don't really see that to be necessary, but perhaps if you're trying to match an answer, then that might be required. But needless to say, that would not be very difficult to do. So what would you have? It would have an x squared, e to the x squared factored out, and you would have that in parentheses times 3 plus 2x squared would be in the parentheses. 42. Okay, once you get the hang of the e's, they're very easy. Of course, this one you have to know what the derivative of sine is to get it completely right. There, I have it written right over here. Actually, I'm going to copy this. Also, I'm going to move it up here to the very first one we did. Doesn't hurt to have it in another place. There we go. So it's going to be e to the sine t times the derivative of sine of t, which is cos of t. So if I'm following that pattern, of course, see I have du dx there, of course, but our variable is t, no problem, same idea. So we would have e to the sine of t times cosine of t, and that would be our derivative. Now, how about the derivative number 43 of cosine of 3e to the x? So what you would look at here is essentially you're taking the derivative of cosine of u, where u would equal 3e to the x. So the derivative of cosine of u would be negative sine of u times du dx, via the chain rule. So we have negative sine 3e to the x times the derivative of 3e to the x, which I move this out in front. So the derivative of 3e to the x would be 3e to the x. E to the x is the only one where the derivative is exactly the same. Not even e to the negative x, because the derivative of the exponent of x is 1. Even a lot of people get confused. If you ask them the derivative of e to the negative x, they would say e to the negative x. Actually, it would be negative e to the negative x, because the derivative of negative x is negative 1. But this one, when it's e to just x, it's exactly the same. So the negative comes from right here, the 3x moves to the front, so you have negative 3e to the x sine of 3e to the x. And notice, I believe I mentioned before, that if you were taking a handwritten kind of class from me there, that derivative notation, very important. Always specify in class, as long as you have showed it, one time. And this might help you when you move on to Cal 2 or someone else, or be a good idea. Now, I always say, as long as you show it once, you can follow the equal sign along. Say if it involves several steps or something, you could do that. But you need to get it in there once. You can't just write it as an expression, because the derivative is a function. Not only is f a function, the derivative of it's also a function. Okay. Integrate. Anytime you integrate something with e, this won't always be true, but the first thing you look for is maybe u is going to be the exponent. That'd be the first thing you want. Because if you get an integral into the integral of e to the u du, that might be the easiest possible integral you could ever have, because you don't even have to do n plus 1 and dividing by n plus 1. The antiderivative of e to the u du is just e to the u. That's it. So anytime you get an integral in that form, you super easy. Can't even make a mistake of misadding 1 or anything like that, which might only occur with negative exponents. I can't imagine that would be a mistake with positive exponents. But all right, so I'm going to let u equal negative x to the 4th and see what happens. So the derivative of that would be negative 4x cubed dx. Okay, that works very well, because x cubed dx is what I'm looking for, for the rest of the integral, except for the e to the u part. It works out really well. So I divide both sides by negative 4. I get negative 1/4 du equals x cubed. So I can replace x cubed dx with negative 1/4 du, which I went ahead and just pulled the negative 1/4 to the outside. So we have negative 1/4 integral of e to the u du, which, as I said before, the integral of e to the u du is just e to the u. So it's negative 1/4 e to the u, which then makes it negative 1/4 e to the negative x fourth plus c. I'll give it a stamp of approval here. There we go. So anytime the e's are in that form, not too difficult. Now this one looks a little weird. I've had this kind of problem on exams, and it's in my notes too. Also, I have one with a radical, I believe, also. But it's kind of strange looking how that's going to fit the e to the u du in this form, and I agree. I agree with that. But to make it a little less strange, what you want to do is rewrite 1 over t to the 7th as t to the negative 7. Bring the t8 to the top and make it t to the negative 8. And now you have something kind of all written up with no fractions or anything, and it's a little easier to sort of focus on. And then we're going to do what I said in the last problem, is let's see what happens if we let u equal the exponent, which in this case is t to the negative 7. Take the derivative of that, would be negative 7t to the negative 8 dt. So that worked out perfectly. So it might have been hard to see at first, but so I got the t in the negative 8. Now I didn't show the step of dividing by negative 7, but that would have been the next logical step. So negative 1/7 du would equal t to the negative 8 d8. So you bring out the negative 1/7. Now you have it e to the u du. So antiderivative, I skipped a step here, but it's okay. Even if this was, if you were having to write this answer out, I would not have a problem with a student going from this form straight to that answer. even though up here, I put like a little intermediate step right there, that's not absolutely mandatory. You can go straight to the answer if you realize what you're doing. So I went right to e to the u and then just put the u right in there. And we've got it. -1/7 e to the, oh, here we go. See the answer. The answer is written with the t to the -7 written as 1/t to the 7th. That makes sense. That's fine. I'm not picky about that if you were having to write that out, but if it's multiple choice, I guess you would expect for that to happen. All right, now here's one where it has e's, but the exponent would not make any sense as being what u should be. Now, what we have to do here is let u be the entire denominator of that fraction. Because when we differentiate it, we're going to get close to the numerator. So if you let u be 1 plus e to the 2 theta, the derivative of that would be e to the 2 theta times the derivative of 2 theta, which would be 2. So e to the 2 theta will be 2e to the 2 theta, which, and this is the way I used to solve these problems. I'm going to get rid of this 2, because the 1/2 comes from dividing both sides here by 2. And so let me get rid of this too. Now it looks correct. So we have basically then the integral of e to the 2 theta divided by 1 plus e to the 2 theta would just be 1/2 du over u. And du over u is covered early on in this chapter as antiderivative of du over u is natural log. And as I mentioned before, remember if that u on bottom is any power other than 1, it's only du over u to the first, you would use the power rule. But this is the one exception where, because, well, the power rule won't work because you would get divided by 0 if your exponent is -1, but this is natural log. Only du over u to the first. So we end up with 1/2 natural log of the absolute value of 1 plus e to the 2 theta. And there it is, answer C, perfect. Okay, so there was a good example of the exponent not being u. This goes back to implicit differentiation. These can get a little messy, but we've already done implicit differentiation. We're just now using logs and e's. So we're going to differentiate all this with respect to x. So the derivative of ln of y would always be y prime over e to y. Just like if it was a derivative of ln of u, if it's not x itself, it's basically, implicit differentiation / chain rule. So the derivative of ln of u would be u prime over u. So it's y prime over y. On the right side, I have to use the product rule. So the derivative of e to the y will be e to the y, but because we're taking it with respect to x, we have to put a y prime. Remember, anytime you differentiate a y, you must put a y prime. So if that was the derivative of e to the x, it would be e to the x basically times 1, so it would just be e to the x. But in this case, the 1 would have to be 1y prime, because you're taking it with respect to a different variable. And then cosine of 8x would just sit there. And then over here, here's your f, which is just e to the y, times the derivative of cos of 8x. You have to take the derivative of 8x, which is 8, chain rule. And then the derivative of cosine is negative sine, so it would be the derivative of cos of 8x would be negative 8 sine of 8x. And notice I have parentheses here to make it not look like it's subtraction. That's important. But then I just move the 8 in front in the next step, which I did that, and I did another thing. I went ahead and moved the multiplied everything by y, which, let's see if I can freehand draw that for you here. Yeah. Okay. So that cleared out the y here. It brings the y into that term and then brings the y into this term. So we have this result right here with that y gone. So there's here and here. All right, now we do the usual. There's not too much stuff here. It just looks bad, but not too many terms to move around. Remember, we want the y primes on one side and the non-y primes on the other. So the least amount of steps to do that would be to move this term here, this y, ey, y prime cos 8x, to the other side and make it negative. And then you have the remaining term, which does not have a y prime by itself. That's perfect. And remember, once you have the y primes collected together, you just factor out the y prime. Sometimes students mess this up when they factor out something and not realizing there has to be a 1 there. I mean, there has to be a 1. Because this, what I factored out, has to be able to distribute to be what's right there above it. So y prime would have to have a 1 there to multiply together to get back to y prime. But I've seen people just factor this out and call it negative without the 1 there. Have to have the 1. Okay, so once you factor this out, you're going to divide by that. So you have the right side, which we did nothing to, left it right there, and then divided by what's in the parentheses here. So you come up here, and there it is. It's answer C. Like I said, these aren't a thing of beauty by any means. But you just sort of accept that, and the answer's going to be ugly, but you don't have to do any kind of complicated algebra trying to simplify anything, or don't do anything crazy. Just come up with that, and you've got it. Alright. This one uses a formula from your formula sheet. The derivative of any numerical base has this formula. In fact, this formula would also work for e. If you think about it, because e is a number. Now we know e to the u is e to the u dx, but this works for that one too, because ln, if you use e right here, ln of e has a value of 1. So you would have e to the u du dx. So that works for e and any number base. It's just if it's not e, you're going to have an ln term right there. That's the only difference between this and e. So real straightforward. The derivative of 77x cubed will be 77x cubed. That will be part of your answer every time. ln of that 77, of that base, and then times the derivative of the exponent, 3x squared. Now, on a multiple choice question, I don't know how they would order the answer terms, but it just has those 3 things, so it could be in a different order, no problem, but it would have those 3 components, a to the u, ln of a, du dx. Not too bad. 49, same formula. I guess I could go ahead and copy that down. Okay. 10. sine of x will be, the derivative will be 10 sine of x, a to the u, ln of your base, which is 10, and then the derivative of that exponent, sine of x, which is cos of x. And that's really it. So these aren't too complicated, I don't think. Here's another one. 2 ln of x. So that derivative will be a to the u, same term, 2 ln of x times ln of the base, which is 2, ln of 2, and then I sort of added extra step here, but the derivative of ln of x, which would be 1 over x. So there we go. So long as you follow that little formula right there, and in case you have to know what the derivative of your u is, if it's your trig function or something, you would have to know that. But other than that, it shouldn't be too bad for these. Now, of course, if something gets buried in a product or quotient rule, that could be a little more work, but would be a little more work. Okay, now we have derivative of log formula. Let's see. So you see what the log derivative formula is. It's 1 over u, ln of a, du dx. And just like the last one, could be modified to work for e, because e is a numerical base. ln is a logarithm, so this also works for ln, because natural log is a log with base e. So if you were doing ln of u and you put e right here, ln of e once again is 1. So you'd get 1 over u du dx, or du dx over u. So there you go. So that would also produce the natural log. So it works for any log. So pretty straightforward. So log base 7 of x squared minus 6x minus 2. The du dx, obviously, then it's written to the side. That kind of means you can put it in the numerator of a fraction, because it's multiplication. So the derivative of what's on the inside, the u, all this stuff, would be just 2x minus 6 over the u, which is x squared minus 6x minus 2. I'll put parentheses around that, and then it's ln of whatever your log base is, which is 7. So you see the du dx was just put in the numerator, and it matches answer B perfectly. Excellent. 52 is going to be a product rule. It's 3x times ln of x to the 6 plus 8. So let's see what we have here. And once again, the order of the product rule doesn't matter, but you may have to reverse, if it's multiple choice, reverse the order of the answer. You see, I just labeled what I did. That I went f prime g plus f g prime. So the derivative of 3 to the x would be 3 to the x ln of 3, but you see, I'll bring that down. Du dx in this case would be 1. So that's why there's not a third term there. Why is there not a third piece? Well, that third piece would just be 1, so it's not needed. Okay. So it's just 3x ln of 3 times g, which is just ln of x to the 6 plus 8, so we won't do anything to that yet, plus the f, which is just 3 to the x. Now we take the derivative. The derivative of natural log is just du dx divided by u. U prime over u is another way you can look at it. So it would be the derivative of x to the 6 plus 8, which is 6x to the 5th, divided by x to the 6 plus 8. And there's how I have it. So only Normally I wouldn't care, but only because we're trying to match an answer here, I went ahead and went along with the factoring out of the 3 to the x. In a handwritten format, I wouldn't have cared about that. And you see, here's a good example of this. It's reversed from what I have it, but it's still correct. So evidently, coming up with this key, they did the product rule the other order, which is fine. Mathematically, that's perfectly valid. So you just reverse these two, and it's exactly the same as answer D. Logarithmic differentiation, which is a technique, and you can use it for complicated algebraic functions if you wanted to, but it has to be used for these kind of functions. When you have a variable in your base and a variable in your exponent, the only way that can be done, there's not a formula, there's not like this, we don't have this, or when you have a variable in your base and a number in your exponent, that's just your power rule when you take a derivative. But when you have variables in both places, you have to use this technique of logarithmic differentiation, which always involves the first step of natural log on both sides. And what the natural log does is that brings down your exponent by log properties. That comes down. Now, let's see if I can not make it look too bad and add a step here. I'll go ahead and put sort of, and I wouldn't care if you actually wrote this step or not, but because I would know what you did. But technically, I'm doing a ddx to this, basically. I'm differentiating the whole thing with respect to x. Now, we saw this come up earlier. The derivative of ln of y with respect to x would be y prime over y. And it will always be y prime over y. So when you're doing these kind of problems, you don't have to even think about it once you get used to it. It's just, that's always going to be y prime over y for this side. There, makes that a little easier. Anything to simplify the process, I'm all for. Now the right side will always involve a product rule. Usually shouldn't be too bad though. So if I go f prime g, like I consistently seem to do, the derivative of x is 1, so nothing goes there. So your g would be ln of cos x plus your x, which is your f, times the derivative of natural log of cos x. All right, the derivative of natural log of u, we've seen, is u prime over u. So the derivative of cos of x is negative sine of x divided by that cos x. So the next step is, down here we multiplied everything through by y. You always bring the y over. So the y is here times all that mess, so I didn't do much to it there. Although the last step I did convert it to tangent, which you may need to do on a multiple choice format. Handwritten, it wouldn't matter. So the y comes up and over, and the last step is you replace y with what it is originally. So just like these ones where you have the a to the u, or e to the u is part of a to the u. You always have that as part of the answer, you know, that term. Same thing here. So for these kind of problems, the original function will always be part of the answer. It's just going to have some stuff along with it. So that will always be true. So in this case, that would make answer A completely have no chance of being right, because only B and D could be right. C, it's just too weird. You would never x minus 1. That's just, they're just trying to see if you would use the power rule or something, but it's just certainly not appropriate here. All right. And so it's just kind of a process. If you're careful, it's not too bad. Here's another one. So the ln of y, ln everything. So you have ln of y, and then that brings, kind of weird, ln of x is the exponent, so it brings in the ln of x, and you have two ln of x's multiplied together, which is strange, but that's all right. Nothing wrong with it. Let's see if I can squeeze another d dx in there. Alright, so d dx, so I said the last problem of ln of y will always be y prime over y. And right side, we got to do a product rule, which is going to have the same two terms, because the derivative of ln of x will be 1 over x times ln of x plus ln of x times the derivative of another ln of x, which will be 1 over x. So basically what you have here is you have ln of x over x plus ln of x over x. So, something plus the same something is always 2 of that something. All right? It's like adding, x plus x would be 2x. So we have 2 of these. This happen to be like terms. That's just a coincidence. Usually these answers do not do that. So we bring the y over, up and over, and then we replace the y with what the original function is, x ln of x. So you have x ln of x times 2 ln of x over x. And I'm just sort of mentioning here that this would be perfectly fine right here, but just in case, though, that you could combine those x's by the properties of exponents. So x ln of x divided by x to the first would be the same thing as x times ln of x minus 1, just because of the properties of exponents. All right. Now we're moving on to integrating a to the u's. The integral of a to the u du. Now, I think I have problems in my notes. I know with e, with radicals, like e to the square root of x over square root of x, that's going to follow the same principle as that. It's going to be a little bit different because we're going to have an ln of 6 in the answer, but other than that, the same thing. See, I brought everything up. So, well, actually, this one was already, so I just wrote a 6 raised to the x to the 1 half, and then brought that x up and made it x to the negative 1 half. So you'll see if I let u equal x to the 1 half, du would be 1 half x to the negative 1 half. So actually what that does is that doesn't put a 1 half on the outside, it actually puts a 2. Let's see if I can. I try to freehand all that, it's going to look terrible. So we're dividing by 1 half, of course, is the same as multiplying by 2, so I'm going to do this. And put a 2 right there. And will it let me grab this? Oh, thank you. There we go. So there's the 2. So 2 du, that fits just right. So we have So you have 2 du and you have 6 to the u du, so you follow that formula. So like I said, the only difference between this and e is we have that 1 over, but like I said before, if it was e, this would work because ln of e is 1 and you have e to the u. So we have a 2 here, so we have to then divide by this formula in ln of 6 because the base was 6, and then a to the u is the answer, so 6 square root of x. So it'd be 2 over ln of 6 times 6 to the square root of x. And there it is. Answer D. Perfect. Alright, not too bad. Alright, looks like we got another one of these. Beautiful. Here a little bit. And let's see. Let u be the exponent. Negative x squared. Du will be negative 2x dx. So we divide both sides by negative 2. So we get negative 1 half du equals x dx. So you see I just brought the negative 1 half to the outside. We have 2 to the u du. So you see come over here. So the antiderivative of 2 to the u du would be 1 over ln of 2 to the u. So we have this 2 on the outside, goes in front. Here's your ln of 2, here's your 2 to the u. That must be negative 1/2 there, of course. And then, of course, we have to replace the u with back to your original variable. You have to finish in your original variable. So that would be, u would be negative x squared. So that looks good right there. Of course, there's actually different ways you could write this. If you really want to be cute, you could combine this 2 with that 2, sort of like I showed you with that problem with the x and the ln of x. But I'm not saying you need to. I'm just saying you could. That could be 2 negative x squared minus 1 up with that exponent. That would get rid of that 2 on front. Okay, that's really not necessary, but wanted to mention it. Took care of 56, here's 57. Now there might be more than one way you can do this. You could probably work with just this formula as far as choosing your u and all that kind of business, but I use this change of base formula, which if that was needed for an exam, I would provide it for you within the problem, most likely itself. Even if it's not on the formula sheet, I could put, hint, change of base formula, and I could write it there. But I did it this way because you see the answers don't have log base 3 of x in there. They're in terms of ln of x. So I use this conversion right here. So log base 3 of x would be ln of x divided by ln of 3. That's if you have to do, like if you had to do a numerical calculation or something. If you had to, and that would also work for log in the calculator. Suppose you had, you want to find log base 3 of 50. You could do it because the calculator only has 2 log bases, ln and log, which is base 10. So you could do either ln of 50 divided by ln of 3, or you would do log of 50 divided by log of 3. Those will be the same answers, I promise you. You can whip out the calculator and check that out on me there and make sure I'm right. But here we just need the algebraic form. So what happens is I'm rewriting the original function before I'm integrating here. So this 1 over ln of 3, I'm just bringing to the outside. This ln of 3 is just a number. I'm allowed to do that. Not variables. Remember, variables can't come out the integral, but numbers can. So you have left with an ln of x over x. And this works out beautifully if you just let u be ln of x. Du would just be 1 over x dx. So that fits your bottom perfectly. Gets it just right. No adjustments needed or anything. So you basically just have an integral right here. The integral is only u to the du. That is it. That's perfectly. And then, of course, you have your 1 over ln of 3. So the antiderivative of, so you have 1 over ln of 3. Of course, the antiderivative of u is using the power rule, 1/2 u squared. So I'll put the 2 out there in front of the ln of 3. And u is ln of x. So it's ln of x squared, not ln of x squared. So the 2 can't come down here. It has to stay there. So that makes it fit this answer by doing it that way. So, and I believe that's the last one. Yes. All right. So good luck, and hope this exam goes well for you.